Hello, in this session we are going to solve certain circuits by using Kirchhoffs rules. So we all know that the Kirchhoffs rules are current law, Kirchhoffs current law, which is based on the conservation of charge, and the Kirchhoffs voltage law, which is based on the conservation of energy. So these are the two laws which we have discussed in the chapter current electricity. So now we will see how those laws can be applied, how those rules can be applied to solve a circuit like this. We have to find out the value of the current flowing through each branch of this circuit. This question is straight from your NCERT textbook. So first we will solve this circuit and write down the values and get the values of the currents flowing through different parts of the circuit. For this particular circuit, we will write only the equations, relevant equations by applying Kirchhoffs rules. We will not go into the details of solving, which is a very simple mathematical process, which you all can do. So let us see how the equation can be written for each closed loop of this complicated circuit. So now, before writing the equations, I want to tell you something, that while applying Kirchhoffs rules, we have to follow certain sign conventions. So let us start with this battery whose EMF is given as 10 volt. So we will write the current that is coming out of the positive terminal of this battery as I1, and the current that is coming out of the positive terminal of this battery as I2. You can write anything you want, whether you can write this as I, this as I dash, or whatever you want you can write. But once you fix a symbol for the current coming out of the positive terminal of the battery, if I say that I2 is the current coming out of the positive terminal of the battery, after all the redistributions which take place in the circuit, the same I2 should enter through the negative terminal of the same battery. Similarly, here we have shown that the current leaving the positive terminal of this battery is I1. So after again all the rearrangements, all the redistributions, the same current I1 should enter through the negative terminal of this battery. So those things you should remember. So let us now mark the current flowing through each branch. I1 is the current leaving the positive terminal of the 10 volt. So let us assume that a current I dash flows through this branch AD. Then the remaining current I1 minus I dash will flow through this 4 ohm resistor. We have applied a Kirchhoffs junction rule at the point A. So the sum of the incoming currents equal to sum of the outgoing currents, or the sum of the currents arriving at the junction equal to sum of the currents leaving the junction. Now let us look at the junction B. Here the currents arriving are I minus I dash from A and I2 from B. So both of them will combine and flow down through the 2 ohm resistor, and the current will be I1 minus I dash plus I2. So now you have a current I1 minus I dash plus I2 entering this junction. Let us call it as E. And we know that the current that has left the positive terminal of this cell is I1. So the same current I1 must enter through its negative terminal. So out of this I1 minus I dash plus I2, I1 has gone into the negative terminal of this cell. So the remaining current minus I dash plus I2 should flow down and reach the terminal D. And from there it should combine with I dash. And the current that enters into the negative terminal of the 5 volt should be minus I dash plus I2 plus I dash, which is I2 itself. So now we have properly distributed the current through every branch. The current which left the positive terminal of a cell has entered through the negative terminal of the same cell. Here I1 left and same I1 entered. Here I2 left and the same I2 entered. And one more point, through the same branch, current will never flow in opposite direction. So if you fix that the current, if you assume that the current is flowing from B to D through this branch, never a current will come from D to B through the same branch. So that is another point to remember. So we have written down the current flowing through each and every branch. Now let us apply the voltage law, Kirchhoffs voltage law. So we will first look for the loop ABEA. So let us write a Kirchhoffs voltage law for the loop ABEA. And what is the sign convention here? You are going along a closed loop, which means that you will return to the same point from where you started your journey. So I start from A. When you are traveling in the same direction as the current flow, the product of the current and resistance will be negative. As I told you, when you are traveling from A to B, you are traveling in the direction of the decreasing potential. Therefore, the current product of current and resistance should be negative. So what I write first is I1 minus I dash into 4. That is for this resistor. Now from B to E, again I am traveling the same direction as that of the current flow. So I write minus I1 minus I dash plus I2 into 2. That is the value of the resistor. And finally I travel from E to A. First I travel through the resistor 1 ohm. Then the product of the current and resistance will be 1 into I1 minus. Why? Because I am traveling the same direction as that of the current flow. Finally, I reach the point A after traveling through the cell. So while traveling through a cell, if you are traveling from the negative terminal to the positive terminal of the cell, you are going to gain voltage, because negative to positive means gain of potential and positive to negative means loss of potential. So while traveling from the negative terminal to the positive terminal, the EMF should be positive. So plus 10 equal to 0. That is our equation for the branch ABEA. First from A to B, then from B to E, then from E to A. So we have written 3 equations for each separate resistor. For each resistor, I have written a separate equation, and combining all of them, we have applied Kirchhoff's voltage law for the loop ABEA. Now let us write the same law for the loop AEDA. So we will write another equation for the loop AEDA. So we start with, again we start from A. This time we are going in this direction, which means that we are traveling in the opposite direction of the current flow. First we travel from the positive to the negative terminal of the cell. So the EMF is negative, minus 10. Again through the 1 ohm resistor, plus. Why plus? Because we are traveling in the direction which the current, in the opposite direction which the current is traveling, which means that we are traveling in the direction of the increasing potential. So 1 into I1, then downward through 2 ohm in the same direction as that of the current flow, minus I dash plus I2 into, here traveling in the same direction. So we have a minus here, minus I dash plus I2 into 2, and finally through this resistor, again traveling in the opposite direction of the current flow, plus 4 I dash equal to 0. That is the second equation. First from A to E, first through the cell, positive to negative, EMF is negative. Then through the 1 ohm resistor in the opposite direction of the current flow, plus I1 into 1. Then downward in the same direction as that of the current flow, 2 into minus 2 into minus I dash plus I2, and finally in the opposite direction of the current flow through 4 ohm, plus I dash into 4 equal to 0. So those are the equations for the first 2 loops, ABEA and AEDA. You may take down these 2 equations in your notebook, and then I will write the equation, final equation for the loop BEDF. I will write the final equation for the loop BEDF. So I shall rub it off. And for the final loop BEDF, first travel from B to E, then same direction of the current flow. So what we write is minus 2 into I1 minus I dash plus I2. Then through the 2 ohm resistor, minus 2 into minus I dash plus I2, and finally there is no resistor here. All you have to do is to travel through the cell from the negative to the positive. EMF is positive, plus 5 equal to 0. So that is your third equation. So first from B to E in the same direction of the current flow, product of current and resistance is negative. Then from E to D, again the same direction as that of the current flow. Product of current and resistance is negative. And finally, through the cell from negative to positive, EMF is positive. So those are our three equations. Now you can solve these three equations for three unknown and get the values of the currents I1, then I1 minus I dash and I2. So you will be able to get the currents flowing through all the different branches of the circuit. So our next question is based on this diagram. We have to find the current in the 3 ohm resistor between B and D. So find the current through the 3 ohm resistor between B and D. So we will solve this problem in two different ways. First we will solve this by using Kirchhoff's law, which is a conventional method. Then we will solve the same problem by a different method, by considering only one battery at a time. So first we will do by using the conventional method, which is Kirchhoff's rule. So let us take this, before applying the rules, let us mark the current. Let the current coming out of the 15 volt battery be I1 and that from the 30 volt battery be I2. Then this is a junction. At this junction I1 and I2 enter. So obeying Kirchhoff's first rule, I3 should be, I1 plus I2 should be the current flowing through 3 ohm. So at B I have applied the junction rule. Currents arriving at junction are I1 and I2 from the two cells. So the current that leaves the junction should be I1 plus I2, which is the required current through 3 ohm. That is what we have to find out. So let us first take the loop A, B, D, E and write down Kirchhoff's voltage law, loop rule. So we start from the point A. So the current is I1. So I am walking through this loop in the same direction as that of the current flow. So minus 6I1 minus 3 into I1 plus I2 plus 15 equal to 0. Why plus 15? Because I am traveling in the direction of the increasing potential through the cell. Negative to positive, EMF is positive. Now let us apply the same rule for the loop BCFD, BCFDB. So this should be ABDEA, it should be a closed loop. So we should end our journey at the same point from where we started. Then only it can be considered as a closed loop. Now let us apply Kirchhoff's loop rule for the loop CBDFC. CBDFC. Then I start my journey from C. The current is I2 minus 3I2 minus 3 into I1 plus I2 plus 30 equal to 0. So I have two equations for the two loops, and let me expand this is my equation number 1 and this is my equation number 2. Then I have to open the bracket and simplify. So what I get will be minus 9I1 minus 3I2 plus 15 equal to 0, and the second equation will be minus 3I2 minus 3I2. So minus 6I2 minus 3I1 plus 30 equal to 0. That is my second equation. Now let us eliminate I2 from these two equations. So we have minus 9I1 minus 3I2 plus 15 equal to 0 and minus 3I1 minus 6I2 plus 30 equal to 0. So in order to eliminate I2 between these two equations, I multiply the first equation with the 3. So minus 27I1, first equation with the 2. So it will be minus 18I1 minus 6I2 plus 30 equal to 0, and your second equation is minus 3I1 minus 6I2 plus 30 equal to 0. Now we subtract the second equation from the first equation and immediately we find that I1 equal to 0. I1 equal to 0. If you subtract this one from this one, you will get I1 equal to 0. I2 get cancelled and 30 minus 30 is 0. So I1 equal to 0. Now put the value of I1 here, you will get I2. So what will we get? Minus, let me put the value of I1 in this equation. So minus 6I2 equal to minus 30 or I2 equal to 5 ampere. So the current flowing through this branch will be I1 plus I2, which is 0 plus 5. So this will be 5 ampere. So the current flowing through the resistor 3 ohm connected between B and D will be 5 ampere. Okay, now we will solve this same circuit in a different way by considering only one cell at a time. Here in the original diagram we had a cell of EMF 30 volt. So I have removed the cell, but I have kept the resistance here. If there is any internal resistance associated with the cell, with a given cell, while removing the cell, you should keep the internal resistance at the same position. Don't remove the cell and the resistance at the same time. So I have removed the 30 volt cell and considered only 15 volt cell in the circuit, present in the circuit. Now let us see what is the current through the 3 ohm. So 15 volt cell, so these two cell resistors are now in parallel. Their equivalent resistance will be 1.5 ohm, and that 1.5 ohm is in series with the 6 ohm. So the equivalent resistance of the circuit will be 7.5 ohm. 3 parallel 3 1.5 plus 6 7.5. Then the current will be, current sent by the 15 volt cell will be 15 by 7.5, which is 2 ampere. So the current sent by this cell is 2 ampere. That current when reaches here will be split into 2. Remember, in a parallel connected circuit, the current always divides in the inverse ratio of resistances. So these two resistances are in the ratio 1:1. So the inverse ratio of them will also be 1:1. So of the 2 ampere that reaches the junction B, 1 ampere will flow through the 3 ohm resistor and the 1 ampere will flow through the 3 ohm resistor connected between B and C. Clear? This is the situation when we consider only the cell of EMF 15 volt. We have removed the cell of 30 volt but kept the resistance at the same position. Okay, now let us see what happens when we remove the 15 volt cell and keep the 30 volt cell at the same position. So I have modified the diagram and kept the 30 volt cell at the same position and removed the other one 15 volt from the circuit. But the resistance 6 ohm is kept at the same position. Now let us see what the current flowing through the 3 ohm resistor is. Before that we will calculate the current sent by the 30 volt cell. So these two are in parallel. So 6 into 3 by 6 plus 3 will give you 2 ohm, and that 2 and this 3 are in series. So the equivalent resistance to the circuit in the second case will be 3 plus 2, which is equal to 5 ohm. So the equivalent resistance of the circuit is 5 ohm and the current sent by the cell, 30 volt cell, will be 30 by 5, 6 ampere. So now the current leaving the terminal, positive terminal of the 30 volt cell is 6 ampere. Now that current, how much of that current 6 ampere will flow through 3 ohm? That is what we have to find. Again, when that current 6 ampere reaches here, it will be divided in the inverse ratio of resistances. Inverse ratio of resistance means the resistances are in the ratio 1:2. So the current will be divided in the ratio 2:1. So we have to divide 6 in the ratio 2:1, which is 4 ampere. 6 into 2 by 3 is 4 ampere. So this time a current of 4 ampere will flow through the resistor 3 ohm. Clear? 6 ampere reaches the junction B. The ratio of the resistances is 1:2. So division of current is 2:1. So the current will be divided as 4 ampere through 3 ohm and 2 ampere through 6 ohm. Previously a current of 1 ampere was flowing through this resistor when this cell was not present. So now when both the cells are present, the current through the 3 ohm will be 4 plus 1, which is equal to 5 ampere, and that is the same current which we had obtained by applying Kirchhoff's rules. Clear? So we have obtained the same current in the second case while considering only one battery at a time. In this problem we have to find the current through the 3 ohm resistor. So this problem can be solved by applying Kirchhoff's rules, but we are going to apply a difference principle called finding the equivalent battery. So how to find the equivalent battery of this circuit, or the combination of these two cells can be replaced with a single cell. How to find the EMF of that single cell, and the method is EMF or equivalent EMF, E equivalent equal to E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. Or we may write it as E equivalent equal to E1 R2 plus E2 R1 divided by R1 plus R2. That is the formula for finding the equivalent EMF of this combination. Remember, here the two cells are connected in such a manner that the positives are connected and the negatives are also connected. If the one of the cells was reversed, then this would have been E1 R2 minus E2 R1 divided by R1 plus R2. So now let us see how this problem can be solved by using this formula. Here our equivalent EMF will be E1 R2, which is equal to 6 into 6 plus 3 into 3 divided by R1 plus R2, 6 plus 3. So this is equal to 45 divided by 9. So the EMF of the equivalent battery is 5 volts. Then we have to find the equivalent resistance of this cell. So what is the equivalent resistance of this cell? The equivalent resistance of this cell can be written as, let me rub this off. The equivalent resistance of this combination will be R equivalent equal to R plus R1 R2 divided by R1 plus R2. These two are in parallel. The combination is in series with the 3 ohm. Therefore, this is 3 plus 2, which is equal to 5 ohm. So what is the current? I is equal to 5 by 5, which is equal to 1 ampere. So first we find the equivalent battery by using the formula E1 R2 plus E2 R1 by R1 plus R2. Then we find the equivalent resistance of the circuit. These two are in parallel, therefore their equivalent resistance is 3 into 6 by 3 plus 6, which is 2 ohm. And that 2 ohm is in series with this 3 ohm. So the equivalent resistance of the combination is 5 ohm. That is the equivalent resistance of the circuit. So the current will be equivalent EMF by equivalent resistance, which is 5 by 5 equal to 1 ampere. So finally we shall solve one more circuit. Here there are 5 resistances which are connected in the form of a bridge. And upon closer inspection you will see that this is not a balanced resistance bridge. So P by Q equal to R by S is not satisfied here. So by reducing this network to a balanced resistance bridge, we cannot solve this problem. For solving such circuits, we have a different technique. It is known as delta to star conversion. So here 3 resistances R1, R2, R3 are connected as a triangle or on the 3 sides of a triangle. Now we are going to replace these 3 resistances with Z1, Z2, Z3, and here Z1 is R1 R3 divided by R1 plus R2 plus R3. Similarly, Z2 is R1 R2 divided by R1 plus R2 plus R3, and finally Z3 will be R2 R3 divided by R1 plus R2 plus R3. So remember these 3 results, Z1, Z2, Z3. Now we will redraw this diagram in the form of a bridge and try to reduce that or try to simplify that circuit by using this technique. Once you find the values of Z1, Z2 and Z3, the solution finding the equivalent resistance circuit will become very simple. So I have redrawn the circuit in the form of a bridge. Now let us replace these 3 resistors 5, 4 and 1 by using the technique that we have just now learnt, the delta to star conversion. So we will draw 3 resistances here. This is the first one, and this is our second resistor, and this is the third one. So this is our Z1. Let us call this as Z1, this as Z2 and this as Z3. So now we write Z1 equal to 4 into 5 divided by 4 plus 5 plus 1, which is 10. So this is 2 ohm. Now next is Z2. Z2 equal to 5 into 1 divided by 4, 5 into 1 divided by 5 plus 1 plus 4, which is 10. So that is equal to 1 by 2 ohm. And finally Z3 equal to, this is Z3, 4 into 1 divided by 10. So 4 into 1 divided by 10, which is equal to 2 by 5. So we have obtained the values of Z1, Z2, Z3 as 2 ohm, 1 by 2 ohm and 2 by 5 ohm. Now let us redraw the circuit. This is our Z1, this is Z2, this is Z3, and the two resistances which were there at the beginning itself remain unchanged. So now we have Z1 as 2 ohm, Z2 as 1 by 2 ohm, then this is 1 by 2 ohm which is present there initially itself, then Z3 is 2 by 5 ohm and Z4 is 3 by 5 ohm which is already present there. So these two are in series, their effectives are in parallel. So now let me erase this and redraw the circuit. So this is our 2 ohm resistor. 1 by 2 plus 1 by 2 is 1 ohm. So this is 1 ohm. Then here we have 2 by 5 plus 3 by 5, which is again 1 ohm. So these 1 ohms are in parallel. So finally you have a 2 ohm and a 0.5 ohm in series. So the equivalent resistance of the circuit will be 2.5 ohm. That is our equivalent resistance of the circuit. So we have reduced a very complicated circuit into a simple form by using the delta to star conversion technique and obtain the equivalent resistance of the circuit.